Okay, let me continue the class. This time I will explain about the dynamics in task space. Task space means actually theta is joint space variable. In the contrary, the x value is task space. So when we learn about the joint Jacobian, we learned about this one. The task space variable x have the velocity and there is joint velocity. In these two variables, there is a relationship which is Jacobian. So this concept can be expanded to the twist. So twist is spatial velocity and joint velocity multiplying Jacobian can be the twist. So using this equation, we can transform this joint space dynamics equation to the task space dynamic equation. So in case of some simple case, x dot equal j theta dot can be time derivative, and x2 dot equal j dot theta dot plus j2 dot theta dot. So this equation. And from here, we can calculate theta 2 dot as a function of Jacobian and task space variable and velocity, joint velocity. So using this equation, we can substitute the theta here. So if we input this value here, then we can make this kind of task space dynamics equation. So this term is about the mass matrix multiplying x2 dot. So in here, original mass matrix multiplying J Jacobian inverse becomes mass matrix, and these terms becomes the velocity product term. Okay, let's expand this concept to the our spatial velocity concept. So in the space velocity, which is twist, in twist, this is the equation, and theta dot become like this, and the time derivative of twist becomes a spatial acceleration, and it becomes theta 2 dot become like this. And if we substitute theta dot theta 2 dot as this equation, we can make this kind of equation. And if we multiplying J inverse with transpose, J inverse transpose, if we multiply this one, and this becomes this, and this term becomes this, and this term becomes this. Finally, this one. When we learn about statics, we learned about torque equal J transpose range. So range equal J inverse transpose tau. So using this concept, we can set this as a range here, and this one equal some symbol, this one. I don't know how can read this symbol, but yeah, this symbol is mass matrix, which is transformed in a task space. So actually, this equation is equation 8.2. 8.21. Let's see the 8.21. Here it is. .21. Okay. In here, this one. We call this n-factor mass matrix. We call this n-factor mass matrix. So this one can be calculated by multiplying original mass matrix and Jacobian inverse transpose and Jacobian inverse. And then this term, so that is velocity product term, becomes simply express eta. And this one is function of twist and theta. Actually, even though the task space inverse dynamics equation, there is variable theta. So theta is joint variable, but in here we don't have theta dot or theta 2 dot, just theta. And other things is expressed with twist. So this one is the inverse dynamics equation in task space. And this one is joint inverse dynamics equation in joint space. So which is having similar form, but actually it contains a little bit different information. So in the case of tau becomes something like torque 1, torque 2, torque 3, torque n. So when we calculate this inverse joint space inverse dynamics, we can calculate this torque value from the theta function of theta dot, theta 2 dot. So in specific theta dot, theta 2 dot, we can calculate required torque. So this is inverse dynamics. But in case wrench, the task space inverse dynamics, we can calculate moment and tau. Moment and torque, force. So this one is rotational thing, and this one is translational thing, and this one has mx, my, mz, and also mx, fx, fy, fz. So this variable came out according to the x, y, z coordinate. But this one came out depending on the joint rotational axis. So this result is about the torque along the rotational axis, but this result some moment and force element according to the x, y, z direction. So if you want to control the robot more focused on the x, y, z direction, so in the case this kind of task space control is more suitable. I mean, if you are making this kind of robot, and this is a humanoid robot leg, think about this is x-axis, this is y-axis, and this is z-axis. So in the case, if you want to use the inverse dynamics, if you want to control this robot using inverse dynamics, you may want to produce some specific force in g direction, and you might want to make specific force x direction and y direction. So in the case of you are moving this leg this or this direction, actually in the humanoid it should have very precise position control in xy direction. But in case of g direction, it is better to control the g direction very softly or compliantly, because for the damping effect. So think this one is some kind of leg, and when you put your foot position, the position is very important. But in the case of g direction, it is better to make very compliantly. So in the case, by using this kind of task space inverse dynamics, we can control this kind of things. So for that purpose, sometimes we need to make task space inverse dynamics. So until now, we are studied about the dynamics. So I will briefly introduce about the modern robotics library using to calculate inverse dynamics. Okay. So import modern robotics as MR. Import numpy as NP. And so in modern robotics library, there is 4 dynamics, and also there is inverse dynamics. Okay, let's see the help command. Inverse dynamics. Okay, the inverse dynamics function, they need theta list, theta dot list, theta 2 dot list, and g vector, gravity vector, and f tip. F tip means some special force applied to the end effector in the m+1 frame. And m list, we need m list, g list, s list. Okay, let's learn this example code. Okay. This one is SATA list, SATA 1, SATA 2, SATA 3, and SATA 1 dot, SATA 2 dot, SATA 3 dot. This one is SATA 1, 2, 2 dot, SATA 2, 2 dot, SATA 3, 2 dot. And then this one is F-tip. This one is moment X, moment Y, moment G is equal, is set as 1, 1, 1, and Fx, Fy, Fg was set as 1, 1, 1. It is depending on the environmental situation. So if there is no external force, it should be 0, 0, 0, 0, 0, 0. And M10, M01. M01 is this one. So in here, we should this one, configuration of actually this kind of things, M01. M01 equal when I equal 1. So M01 is configuration of 1 frame in 0 frame. So the homogeneous transformation matrix in a 0 position from frame 0 to 1. And this one is frame 1 to 2, and this one is 2 to 3, and this one is 3 to 4. So actually, this one is large SE3 and homogeneous transformation matrix, which is the theta equal 0. Theta equal 0. So this one should be calculated, somewhere. But in this example, just we used this value. And then this one is G list. G list means the spatial inertial matrix of I-link. So actually this one is diagonal matrix. So actually this one having this kind of form. Yeah, actually spatial inertial matrix G equal IB 00 MI. So actually this 3 value is this, I didn't indicate this one. So some 3.7, 3.7 like this. And this one becomes like IXX, IYY, IZZ. IXY, IXZ. So this kind of things is here, but this value was this value is 0, and only this value was having this value. So if you see the actual value, okay, I will run this one. If you see the actual value, something like this. And making these things with a list, and this is a screw axis list. And then we can run this function. Then we can see the joint torque. This one is Newton meter, tau 1, tau 2, tau 3. So this inverse dynamics library very fastly calculates these things. So we saw the simple example to calculate inverse dynamics in some Sera, Serada, Seratuda condition. So actually, to learn this function, we have to know this kind of precondition, these things, and also these things. So in the practical use, we may have to calculate this one. But for the simple example, we just learn like this. So that's it. Our class is over. Okay. Until now, we learned about the modern robotics library, modern robotics. Actually, I'm sorry. Let me see the modern robotics textbook. Okay. We learned about the rigid body motion and forward kinematics and velocity kinematics and statics and inverse kinematics, and we skipped closed chain kinematics. So we just skip and we learned about dynamics of open chain. And then there is some kind of trajectory generation and motion planning and robot control things. And there is grasping and manipulation and field mobile robots. So these are later part of the modern robotics. So we finished about our class until the dynamics of open chain. So I hope this class is, I hope that this class is very, it might helpful for your project or for your study and for your understanding about the robot. And so basically we learned about the screw and screw theory and screw based something. So all the dynamics or kinematics things was done by the twist and screw concept. So it might more complex or it might more simpler than before, but basic concept of twist is to describe the rotational thing and translational things is represented together. So for that purpose, this class was done. So I hope you that this class was helpful for your goal. Okay. In the next semester, I will open the robot control class for the for the graduated student. In that class, I teach the later part of modern robotics textbook. Actually, trajectory generation and modern motion planning and robot control and field mobile robot things is taught on the robot control class. So if you are interested in that class, I hope you to take a lecture in the next semester. Okay, and also the GitHub library will be this one. This library also will be updated
if I have some time, so I will upload the inverse dynamics things in here. So if you have continuous interest about that, you might visit sometimes and check updated things. Okay, thank you for your studying, and thank you for your operation. So my lecture sometimes, actually many times, lated to upload. So I'm very, very sorry about that, but okay. Anyway, thank you. See you next time in somewhere. Okay.